Okay, guys, I know this is a long lesson, just hang in there. So, Theorem 5.34. If f is continuous on negative a to a, and I try to draw a picture down here, like I said, don't judge my sketches. I know they're terrible, but these are going to be the same. That's the same curve. It's symmetric. If it's an even function from negative a to a, then f of x dx is going to be 2 times the integral evaluated from 0 to a f of x dx. So basically, um, we'll talk about that in a minute with this picture. If it's an odd function, then from negative a to a, then f of x dx is going to be 0. So, and that makes sense. We'll start with the one that's the easiest. If we looked at the area of this, and we subtracted out from negative a to 0, and then from the other side, if you subtract them, it would be like the yellow region minus the blue region, which would just give us 0. Okay? If it's an even function, then we would have this region plus this region, which would just give us 2 of those regions. Okay, let's see an example. Evaluate use theorems for even and odd functions. So it wants us to apply those theorems. I see it's from negative 1 to 1. 1's the negative 1 to 1. We can see from negative a to a, negative a to a, that fits the theorem of f of x dx. So the first thing we need to know, is it going to be the even? We're going to get 2 times that value, or is it going to be the odd to where it's just going to zero out? And the way we determine if it's even odd is just like we did in pre-calculus, and evaluate the function at f of negative x. So pause your video and do that now. Okay, negative x to the fourth is just going to be positive. This right here would simplify to positive 3x squared plus 1. We can see that f evaluated at negative x is equal to f of x, exactly, term for term for term. So this is an even. So we're going to now use our property by the theorem. So we'll say 2 times 0 to 1. Make sure you pull that from the theorem, because these lower limits and upper limits change to the theorem. So 2, 0 to a. So we got 0 to a, and then we have x to the 4th plus 3x squared plus 1 dx. And now we can just evaluate this. So let's evaluate this. So I have this 2 x to the 5th divided by 5. Finding the antiderivative now. So this is x to the 3rd divided by 3. We just simplified x to the 3rd plus x evaluated from 1 to 0. So now go ahead and plug those calculations back in. I'll pause it and then you can check your answer. Okay, did you get 22/5? Okay, I hope so. I didn't plug all that in here because it was just 0, so we can do that. Okay, this is our next example. It's negative 1 to 1, so it fits our property. We need to test to see if it is going to be even or odd. So that's the first thing I want you to do. Okay, when I evaluate this, f of negative x, everywhere there's an x, plug in negative x and then simplify. I get negative x to the 5th, which is opposite, negative 3x to the 3rd, opposite, negative x, opposite. So term for term for term, everything's exactly opposite. So that means that this is an odd function. Using our property, then from negative 1 to 1, x to the 5th plus 3x to the 3rd plus x dx is just going to equal 0. And that's very nice property to have there. Alright, let's see our next example. Alright, write that down, and first of all determine if it's even or odd, and then see how far you can get. Okay, so when we evaluate f at negative x on this one, each term for term for term, we didn't have that consistency that we had in part A and part B. So we want to look at these individual terms, because remember, we can take the integral of each single term, because we have a property to do that. So if I wanted to group this 2x cubed and negative, so that looks like it would fit the odd property. This one individually would be when you evaluate it at negative x, we got the exact same thing, so this one appears that would fit the even. This specific term in itself would be odd, so if I chose to group the two odd terms together, I could rewrite this as negative 5 to 5 of 2x cubed plus 7x dx, and that would be my odd terms. And then I could say plus negative 5 to 5 of what? Our even term, which is just 3x squared dx. Okay, now this is going very extensive into really trying hard to make use of our properties. We could always just evaluate this integral as is using our previous examples, but we're specifically told to use our even and odd theorem, so that's why we're doing that, making efforts to do so. Okay, well, if this is the odd, we remember that what's our odd value going to equal to? If it's an odd function, it's just going to be 0, so that would give us just 0 here. And then for the even function, we would rewrite this as 2. Evaluate it from 0 to 5. Now remember, this is, make sure you make special note of that. 0 to 5. And we changed that. Let me tell you why. Because we're going to say from here to here, and we're going to double it, because remember, these are the same region. So that's why we're real careful to make sure we make that adjustment there. And then we have 3x squared dx. Now we're just ready to go ahead and evaluate this. So let's take the antiderivative of this term, which would be x to the third divided by 3, and then of course our 3's would cancel, so we just have that. Our 2 that's out front, and our upper and lower limit. And then so we just get 2, 5 to the third minus 0 to the third, which is just 0. So that's going to be 2 times 125 equals 250. Alright, we're back to another theorem. 5.35, let f be continuous on the closed interval a to b. If a is less than or equal to c, which is less than or equal to b, then we have the derivative, the integral, is equal to the function. And we talked about this in a previous lesson, so just to see it one more time as a theorem. And then also we see this, if you have if g of x, capital G of x, is defined by this, then we can find the derivative of that, which would basically just give us back our original f of x. So the derivative of an integral is equal to a function. It's just a restatement of this particular theorem. The derivative of an integral equals a function. And another theorem that was in a previous chapter is a mean value theorem, and we worked on that. And basically it's just saying the integral of f of x dx from a to b is also the f of z times b minus a. Alright, before we go any further, let me just stop for a minute in case you don't remember the mean value theorem that we talked about in Calculus 1. Remember we said if we had some function, let's just say this is our function in red, and we said here's our a to b over here, our intervals, and I checked from here to here and I drew a secant line. We said that the mean value theorem said that there's also some point C in which the secant line from A to B is also equal to the tangent line at this point C, and we would find out what our C was, and we were given formulas. Similar idea here, but now we're going to use it for integration, and instead of a C we're looking for Z, just so you don't confuse the two. So hopefully you remembered a little bit about that from Calculus 1. Now we're going to apply this formula that's given to us in this particular theorem to work this next example. Oh, let me make a page for it. Okay, here it is. Find a number z that satisfies the conclusion of mean value theorem. So here's our mean value theorem for the given integral. And then part B, find the average value of f on a to b, which let's stop for a minute and write the average value theorem down as well. So the average value is going to be denoted by 1 over b minus a of our integral from a to b of f of x dx. So we're going to work with two new given theorems and definition formulas. So we have a mean value formula that we were given, and we also have an average value theorem. So pause these and write these down. And here's our example, and we're going to cover part A is the mean value and part B is the average value. So pause this for a second and write this down, and we're going to work it on the next page and the next video.